I'm Ed Doe. I'm the VP of Product and Business at Barefoot. I've been at Barefoot a little over 4 years. We started the journey about 5 years ago and very much had the pleasure to present to this audience, as Tom said, a little bit over a year ago. First, before we went into the details about what we're doing with respect to analytics and deep insight, I wanted to give you guys a little bit of context about who Barefoot is and how we fit into the overall scheme of things. And so I'll start off with that, and then I'll turn it over to my colleague Roberto to talk about analytics. So what is Barefoot about? We're really focused on trying to change how networking is built. Today, we feel there's a fundamental challenge with networks being dictated by the functions and the data planes that are hard-coded into the fixed function switches. You can write all the software you want to at the higher level, but unless that protocol or the way the packets are handled are supported in the fixed function switches, you can't change that. And so we want to change networking into a much more user-driven approach, as well as a software-driven approach. And so we're changing this, and we talk about it, changing it from a bottoms-up to a tops-down approach, and allowing the users and the applications that run on those networks to dictate how they want the packets to be processed. And so what we're doing at Barefoot is we've brought about this programmable switch technology, and we want to talk to you about some of the applications about how this is impacting the world of networking. So one of the analogies that we talk about what we're doing, it's really about building a domain-specific processor for networking. And so transformations like this have actually happened in a number of other industries and recently applied to some other ones where programmability and this concept of being a programming language and a compiler have impacted many other industries. If you go back 30 or 40 years with the advent of modern programming languages and instruction set architectures, that happened with CPUs. And then for those of you that are geeks in other fields, this has also happened for digital signal processors. But most recently, a lot of people talk about GPUs and a lot of new applications. And so GPUs have been getting a lot of interesting coverage in new market applications. And if you really think about what companies like NVIDIA and AMD, ATI did, is they brought about programmable graphics processors, and they introduced an open programming language that allowed people to repurpose these GPUs for new applications. And now you hear about GPUs as being the engine that is powering, for example, all of the new things in machine learning and deep learning. But that's already evolved in just the last 10 years to where now you even have machine learning processors specific to this. And now with open programming languages like TensorFlow, you can repurpose that to a bunch of different machine learning applications. So if you think about what Barefoot is doing in the context of networking, we're doing something very similar. So we said we had to bring about a programming language. That programming language is P4, an open source programming language that is community owned and now is moving into the Linux Foundation. We had to have a compiler. That's an essential component of all of these different fundamental transformations and all of those other ones. And then the last piece is Tofino, which is our programmable switch architecture that is just as performant, just as power efficient, and just as price efficient or price effective in all of those markets as well, being able to allow for programmability to take hold in networking. So I wanted to tell you a little bit more about these components and what each one of them brings. First is P4. And so P4 is owned by the P4.org consortium. This is an open, independent consortium, and as I mentioned, it's now part of the group of projects that the ONF owns inside of Linux Foundation. And it's really been growing. It's been an open source project for the last 3 to 4 years about creating this mature open programming language that can be used for multiple targets or programmability for wherever networking is used overall. And so the P4.org group, it's a free Apache consortium, very much like many other Apache projects, or one that's very near and dear to this community here, Open vSwitch, which is also an open source Apache project that's moved into Linux Foundation. And it's a free open source project that allows all the different people to be able to leverage this language for their applications. What's really impressive is we're talking about the networking community, that hasn't been this concept of programming as much before, but there's now already 1,500 developers that have been directly trained by P4.org in this P4 programming language, 5,000 commits, a lot of followers, a lot of forks, and a lot of applications to a lot of other projects. So much so that there's now been actually 200 contributions, 30 different repos for different projects, and there's actually now over 10 different targets for where you can compile P4 down to, not just the Barefoot Tofino series of devices. And the organization is not just composed of individual developers, which are the bread and butter of the new networking community, but also it's been backed by over 100 different large organizations, ranging from advanced research organizations in academia to 90 of the largest players in networking, ranging from large hyperscalers like Google and Microsoft to large network equipment manufacturers, as well as many different people that provide programmable targets as well. So that's one component where we see ourselves fitting in the stack, is we're providing programmability at the leaf and spine or the switching layer of the network, where programmability really hasn't existed before. But programmability has also existed in terms of FPGAs for transport or NPUs for routers. But programmability is now extended all the way down into the server with the advent of now smarter and smarter NICs, where people can program and add networking capability to the NIC side of things, as well as OVS or the vSwitches, and then even into the Linux kernel or the operating system itself with programmable components like eBPF. And the beautiful thing here is that P4 has proven itself that it can program and compile down to each one of these different ones. And this is where there's now commercial entities behind every single one of these different projects, which has adopted P4 to leverage it for their own needs as well. And so this is where we see programmability in P4 coming to the entire networking ecosystem, all the way from the server out through to the transport core of the network as well.
So, just a quick question.
Sure.
In regards to, because on the sort of Linux contribution side, with CNCF, right, with CNI, is any work going on with P4 with CNI in terms of container abstraction for what you can do with P4? Because that becomes really interesting.
Sure. At this point, not directly with CNI, but where we have seen the applicability to container networking is to Linux core networking modules like eBPF or even TC, where those have the ability to modify networking traffic.
Sure.
And so now that there's a P4 compiler to those components natively exist in container networking abstractions where there is no vSwitch, for example, or no hypervisor. And so that's the place that we've seen this. Or it could be in a place where there's a smart NIC and no hypervisor as well, from that side of things.
Cool.
But not directly with CNI and CNCF.
A quick question.
Yeah.
If someone wants to learn about all of this, there are tutorials, of course, but are you aware of any emulators that people can learn P4 against?
Sure. Actually, in p4.org, one of the fantastic things about that open source consortium is that there are network simulators that you can just load into containers or into frameworks like Mininet, where you can actually go build an entire network of multiple programmable nodes to emulate leaf switches, transport co. And even large companies like Microsoft have actually adopted the P4 soft switch into their Azure network emulator, and they're now starting to provide ways to test this out, obviously in tandem with Sonic, which is their open operating system, and be able to test this out at network scale. So now there's ways to start to emulate large networks, not just one switch at a time, but hundreds of network elements.
They've got a full lab up on P4 in their GitHub repo that you can actually fire everything up and play around with it all.
That's exactly
good to know.
And the beauty of it, it's not just the programmable switch in the P4, but it's kind of a full ecosystem with an operating system that allows you to actually establish adjacencies and protocols and everything else.
Are there other cloud providers, Azure and GCP, who might be leveraging this in addition to AWS or GCP in addition to Azure?
So Azure right now leverages it more as a lab or a way to go do it, and so they're offering their infrastructure, where you can easily spin up large number of containers to do this. And so it's more on the research side of things. Today, I think Azure has done this because they want to provide a proving ground for that. We see, though, that framework arguably could be extended to many other operating systems or even data planes as well.
But no plans in the talks right now, like the investments already being made with Microsoft.
Exactly, that's correct. So the second piece that I talked about is to make this a viable ecosystem is not just the programming language that has been adopted by multiple parties and commercial entities here, but you need to now have a programmable entity that is just as performant as what you've had today. Because nobody wants to trade off and lose out on performance or power efficiency or even cost effectiveness. And if you look at all the other major transitions, they NVIDIA had to come into the market and provide a programmable graphics processor that was just as good as all the other great graphics processors that have been hard-coded as well. So if you look at how we've approached this, today how do people build high-performance, power-efficient switching devices? They build them in this fashion where they have a pipelined architecture that allows you to deal with the different stages of a packet and the different headers that are there. And you have a fixed parser that parses those headers out and then allows each stage to operate on those. There's memories associated to those and then different actions that you would do, encap, decap, ACLs, drop, deny, those kinds of things. But each one of these stages is hard-coded. And so that means every time there's a new protocol that comes around, like VXLAN, one very relevant to this audience, it takes 5, 10 years to allow for that transition to happen because the chip has to be rebuilt, the software has to be done, the new hardware has to be redeployed, and those kinds of things. Or even if it comes down to there's a new network paradigm, for example, that I need 10 times the table size or 2 times the table size of what I had before, then again, just even changing the table sizes takes a long time. So what we've done with our programmable architecture, we said this is the way that you build high performance, power efficient devices, but we said, why do these elements need to be hard coded? So we have a programmable parser that allows you to pick out any header that you want to, even new headers, for example, VXLAN NSH or Geneve extension headers or V6 option headers, and be able to extract those, or even just pull out different bits from those headers and be able to do that. And then you have the same concept of stages, but those stages in the pipeline are all programmable. Programmable from the memory, the type of lookup, and the actions that you have on there. So what you can do is you can actually make this look just like the diagram above, right? You can program the stages in the same fashion to have L2, MPLS, L3, ACLs, tunnels, and so on, or even reverse the order of those, or for example, get rid of some of those because maybe some of those are not applicable in all of your environments. But you can do that, but you have now the flexibility to do this at high performance and with the same characteristics of a fixed switch as well.
So does this give us flexibility to increase like maximum MAC address tables or spanning trees, so on and so forth, basically?
Yeah,
and we can actually control. It's not like 64 and you're done.
That's exactly.
Like running out of TCAM space. That's a pretty common problem.
Right.
Those two are perfect or great examples. So if you wanted to have more VLAN bits or VTEP entries, for example, in a virtualized environment, or where before one of the classic things with even the advent of VXLAN was first people said, okay, I support VXLAN, but I don't support VXLAN routing. That required a complete change because you needed not to only do one lookup on VXLAN, but a second one. That required a lot of hardware to be refreshed. You could do that, and then you could say, maybe I want to have, instead of 1,000 VXLAN tunnels, now I want to have 16,000, for example. And that's been a very common use case that allows the network to dynamically adapt to the resources. Think of the network resources now are adapting to the proliferation of new applications, whether it be containers, for example, in a non-VM environment, or more VMs or tunnels that you need as well, or more ACLs that you were talking about.
So what about FCOE?
So FCOE is another good example. That's different kinds of encapsulation. It starts with Ethernet, but then it's a different type of header. You're not going directly to, for example, an IP or an MPLS header. You're now going to that fiber channel header. And that's another perfect example of another change that could have been enabled without having to replace all the hardware just to be able to support awareness of those protocols. Now, FCOE, of course, was developed in a way that kind of normal Ethernet fabrics could deal with it, but to have true awareness, you wanted the switches to be able to identify, be able to apply ACL policies, enforce security at all of the layers as well.
So could this give us flexibility in establishing a multi-tenancy model in a single tenant for purposes of microsegmentation?
And that's another great example that we've seen is people want to be able to scale the number of multiple subtenants that they have, or be able to use a different identifier to be able to separate tenants from each other. Where today you'd normally assume, oh, it has to come with a different VLAN tag or maybe a different VXLAN tunnel. Now you can choose to have a combination of the two, even be more efficient and maybe use portions of the V6 address, for example, to say this is the tenant identifier instead of using the VTEP address or the VTEP bits as well to go through that.
And with how you've got the tables and you can break them up, I could technically establish out a smaller tenancy and space for one so that it keeps the memory requirements down. But for some others, I can have it be rather expansive because it has the requirements too. That's
exactly. And so you see that where we see applications of this, that's a perfect example is maybe you need a smaller number of multi-tenant bits in one part of the network, but then deeper in the network you might, because you're now aggregating hundreds of tenants up to a different place, you might want to add a much larger space or table memory associated to that deeper in the network. And the beauty here is now you can use the same piece of hardware, just with different profiles or P4 programs, just like you can use that same GPU to do inference and then a different program to do training, and then also be your greatest video gaming engine at the same time, right? And allocate your resources that way. The same thing applies here. You could technically use that same piece of hardware and with different P4 programs, adjust it to the different requirements for different places in the network.
And you can flexibly change that on the fly.
That's correct. Just like you can upload.
Really on the fly?
Yes, absolutely. And so that's what's one of the unique aspects of our hardware, is that you can upload new programs to it hitlessly and be able to update those kinds of things. And so that's a common requirement. Is in many cases you might want to increase the amount of resources, without bringing down your network.
We didn't realize this application was going to do so well. We need to throw more resources.
Exactly. Now, typically in some cases where you might be doing this, and you might want to install a brand new protocol, that's probably going to require, from a network perspective, some amount of network downtime, because you're going to want to make sure all nodes in the network understand this new protocol at the same time. But one of the common applications is I just want to allocate more memory to the existing application, and that can be done hitlessly.
Well, and one other part where we have the MPLS tables listed above, I'd be really curious how that actually would play into it, but not looking for specifics. That's just in
right. In principle, that's exactly it.
Does all of that also mean that you've got one switch and then you want to say in a way virtually divide it up into 16 switches, which are completely isolated from each other, so traffic doesn't cross, of course, but you can use it with 16 customers, for example?
That's another perfect application, right? So you can actually segment these resources such that the resources are not just with a multi-tenant identifier and then effectively sharing the same table. You can actually instantiate multiple copies of the same table with different sizes doing the same function, but isolated by different individual tenants. And so you could even think of it as you could have resources allocated specifically to one tenant. One tenant might need MPLS, the other tenant might not, for example. And so you can partition that as well. And so the hardware contract as well allows you to do that, because underlying it, there's this concept of pipes and locality to different ports.
Architecturally, I'm concerned around memory namespace or namespace sharing, so we don't face something like, what was it, recent meltdown, Spectre type of things, but within the network stack.
Right.
Not to say that is the case, but I'm curious how it actually is architecturally carved up.
So that's one of the aspects of the programming language that's already evolved over time. The first instantiation of P4 didn't have this concept of, different namespaces from that side of things. And so the programming language has evolved P4. It's had iterations and feedback from a lot of folks. And that's one of the recent things that was added in the 2016 version of the language, to add different namespaces from that side. So that you can have hard partitioning of these things from a physical resource side of things as well as from a namespace.
Because in reality, on traditional switching architecture, I've run into problems where I've got duplicate MAC addresses, even though I don't have duplicate MAC addresses.
Exactly.
It causes MAC storms and so many problems.
Exactly, and that's a perfect example of where you'd actually want to have separate actual tables, so that
tenancy within the switch stack. Basically.
And so in that case, you'd actually have, for example, you'd break up this engine right here, and you'd allocate 3 of those modules right there in memory for one copy of a MAC table, and you could allocate 2 or 1 for another copy of it, and they could each have the same exact MAC address that wouldn't cause collisions and other challenges in the data plane.
Cool.
But these are all fantastic examples of how programmability is really enabling a lot of transformations across a lot of different industries as well. So going back to and trying to give you a sense of where this has gone, and I think I've alluded to this, if you think about what happened in graphics for the first 10, 15 years, I know people here were talking about a LAN party and playing video games that might be pretty resource intensive on the graphics side of things. In the early days of graphics, it was really about enabling this new capabilities that were on the graphics side of things, more advanced 3D engines, or even in professional graphics. But then once this model got established with the programming language, the compiler, and doing it, it started to reach into new markets like augmented reality, VR, HPC, big data. And those really were the precursors to what everybody talks about now with companies like NVIDIA and GPUs, which was self-driving vehicles, right? Or, machine learning from that side of things. So to paint that picture here, obviously, we believe we will be the best, switching substrate from a programmable perspective for all of the different markets, whether it's enterprise switching, data center switching, telco, cloud, those sides of things, as well as the great substrate for telemetry and analytics that we're going to touch upon here. But down the road, we still don't know what are the massive transformations that are out there, but we're starting to hear some of the early things, which are things like enhancing layer 4 load balancing and building that right into the switch, or firewalling, or packet broker functionality, and bringing all that in. And down the road, maybe it means that there's going to be new interconnects for machine learning, right, that are needed. There might be new protocols to be able to accelerate machine learning workloads. And we've already started to see interesting papers around this as well to explore some of these ideas, or even storage and that. And down the road, who knows from that side of things. So today, where are we, and where can you get your hands on Barefoot Tofino-based platforms? We have a full family of devices that goes from 1.8 terabits all the way up to 6.5 terabits that are based on P4 and PISA. So the first of these, the OEMs that came out with the product, Arista announced the 7170 series of products in a couple of different SKUs, different densities as well. They're using this for some of the cases that you guys talked about, enhanced tunnel scale, application telemetry, doing things that couldn't be done before in regular switches like large scale NAT or network security, all leveraging that Barefoot programmable pipeline, and they've only just started to peel back all the potential possibilities there. The other partner that's announced a platform is Cisco with the Nexus 3400. There's a 1.8T version, which is 481025 with uplinks. And you can see here that similarly, they talk about data plane telemetry as one of the key capabilities that they're enabling, as well as different engagement models with customers as well. So this is part of their Nexus 3400 series, newly announced from that side. And then, of course, one thing that's obviously much talked about in the networking, we're very active with the white box ecosystem with large cloud scale providers that do their own. We talked about Sonic as one of the open source operating systems supported here, but also other companies like IP Infusion, a wide variety of different systems from different white box manufacturers as well.
So how does the Tofino ASIC, as basically functionality, compare or contrast when it comes to certain type of workloads? I like to think of the Fortinet NPUs and the content processors for optimized for SSL traffic versus optimized for network type traffic loads. Are you able to kind of do equally well, or we do one really well and the other one we do a horrible job of?
So the Tofino device isn't really focused on SSL or encryption workloads, so that's a good differentiator. So it doesn't really play into the arena of where some of these NPUs, like the Fortinet devices or others that do handle encryption or termination of those kinds of workloads. It's really focused more on doing think of like the workhorse of switching that's done in a lot of the typical top of rack, leaf spine, data center type environments. Now, as we talked about, there are some functionalities that could be offloaded, like layer 4 load balancing and firewalling, but not in a case where it would involve a lot of encryption termination from that side.
But you
so
guys
in the middle.
So those things are not as well suited for the Tofino architecture.
But you have a fast enough bus on this in the architecture that you could actually, if they wanted to, someone could build a box that was a pipeline redirect straight out
I would
and right back
agree,
in.
except when it comes to SSL decryption, especially at high scale.
Yeah.
Just because of the
Why not scale a set of
mathematics
GPUs
involved just around that portion.
Yeah, but you can build a set of high-scale GPUs that sit right next to the Barefoot chip on a switch and do it right there if you want. If someone wanted to build it, I mean,
If someone wanted to build it.
if someone wanted to build it.
And so those are probably the
possible.
next generation of potential hardware that could be.
So it's not the target today.
Today, it's not the initial platforms, but obviously as you go into more advanced network functionality, those are definitely things you'd want to have the performance of this coupled with some of the advanced capabilities for SSL or full packet payload inspection, like think of regex.
The real question is, where do you want to offload? Do you want to offload in the backplane, or do you want to offload the server?
Put in context, if we were having this conversation 3 years ago, we're looking at like 10%, maybe 20% SSL.
Yeah.
Today I'm looking at 90% of all my traffic.
Right.
That is
Sure.
HTTP is all HTTPS.
Yeah.
And that's why I just have to look at it from that standpoint, both internal, east-west, as well as egressing out to the internet.
Right. So
Can
hopefully,
you go back to the Cisco
Sure.
slide really quick?
yeah,
That was the 3400.
yes.
Are there any other integrations you're expecting?
Yes, absolutely. These are the first two major OEMs in networking that have brought these products to to market. And so we're really working with many other networking OEMs as well as people that are exploring using this in different network applications. Think of in the network packet broker space or layer 4 load balancing. Those are other future ones where you could imagine things coming over the next 6 to 12 months and beyond as people start to marry a couple of devices together.
Specifically with Cisco, the 9300 platform, any integration?
No, in fact, right now this is strictly in the Nexus 3400 series of devices.
Do you have a white box option outside from this? Because I know that if I want to license MPLS in these cases, I probably cannot, or it'd be a heavy license cost, whereas a white box, and it's like, just turn that feature on.
Yeah, and that's one of the things that a company like IP Infusion has a very strong MPLS stack offering, and then there's a bunch of different white box vendors as well that have built platforms, or ODM vendors that have also built.
Oh, excellent. So IP Infusion has, where you guys are integrated to actually use your ASIC on the platform for the white box.
Exactly. That's excellent. And IP Infusion is somebody that I think has spoken in this environment before, and they're well known for their carrier grade protocols as well. Yeah, and then they would be built on one of the other pieces of hardware white boxes that are out there.
They write the OS for everybody. So.
Yes. So the main thing that we wanted to talk about today was data plane telemetry. I think you've touched upon a lot of these things: the flexibility, the future proofing, the scaling, the simplicity. Really, it's counterintuitive, but one of the things that programmability allows you to do is really simplify your network. But the one that we're really excited that's most applicable to virtually all networks, applications, and workloads is data plane telemetry. This is something that is universally applicable to many folks, and this is where I'm going to turn it over to my colleague Roberto Mari to talk about Deep Insight, which is this new product, and give you a sense of how that technology is being brought to bear.